so maybe just one two words about myself. I'm working for IBM Research in the Zurich lab. This is a town called Rüschlikon, very close to the city of Zurich. And I'm there since 2023. Before I was working for the IBM Business Unit for more than a decade. And I started with implementing a geospatial tensor lakehouse, which we open sourced and which is now an official IBM Research product. Which you can license in the enterprise version or which you can use in open source in the non-enterprise version. And now recently I moved to the modeling side. So I'm the development lead of a tool called TerraTorch, which is fine-tuning and inference toolkit for geospatial foundation models. So what we do in our group is a lot of computer vision, and especially computer vision for Earth observation data, so satellite data. So those images are special because they have more than just 3 bands. And they are also sparse because the satellite is recording the planet in spots. So you don't have an image for each position and each timestamp. That's also something you need to deal with. Okay, so let's share the screen. Okay. Let me find the presentation. We will have some demos later. Or we will mainly have demos, just a couple of slides to set the stage, basically. So, okay, so here are my colleagues, some of my colleagues. They are basically driving a lot of that stuff. So, as I said, I'm more on the TerraTorch tooling side. So, all those models have been developed by Paulo and Benedict and a lot of others. And also, I will show you one, let's say, sample application where we are actually using the stuff which we open source in our commercial product that's driven by Blair. So you see here we had a shift. The shift basically was when the paper was published. Attention is all we need. No, that's basically, you can see it as before Christ and after Christ. And the introduction of transformers transformed a lot of the AI and deep learning space. So that was one thing. And the other thing is, maybe you remember transfer learning, where you actually use the pre-trained model, which has been trained on a specific task, and just you cut the last n layers, and you put your own layers there, and then you continue to train the whole thing again with your use case data. And from that idea, the foundation model idea stems from, basically. The idea is, in the foundation model, you train a model for transfer learning. The foundation model is the base model, which we call the backbone. And then you have task-specific extensions to that model, which are really, really small. That means you need to train only a little more. And then you get actually a model for your specific task. And what you see here is a kind of overview on all this. So you have the pre-training phase at the top. So you need to make sure your data is accurate. If you train the foundation model already with wrong data, you get wrong results, obviously. And the idea is it's self-supervised learning, because labeled data is always a problem to have, no? And in foundation models, the trick is basically that it learns reconstructions. So you mask out data in the target, and the model needs to reconstruct the data. It's basically an autoencoder style of architecture. And it's going that far that we mask out more than 95% of the data, and the model still is doing a great job in reconstructing the data. It's quite impressive. Once you have this pre-trained model, you take the encoder. You can basically throw away the decoder. This was only necessary for the reconstruction and the training in most of the cases. And then the encoder becomes your backbone. And then in the fine-tuning, what you do is you add task-specific decoders and heads. So decoder is just a number of layers, and then the head basically turns the whole model into, for example, a regressor, classifier, image segmentation head or object detection head, and so on and so on. So this fine-tuning happens with label data. So you need only a small amount of label data because all the knowledge about the domain has been encoded in the encoder during pre-training. And once you have fine-tuned, you will get a model which you then can use for inference. So that's ordinary stuff. Now, from the inference side here, it's not different to any other model. The only difference is the way how you obtain the model. By pre-training one part, attaching another part, by fine-tuning the other thing, and then you get the inference capable model. So our latest release on the Earth observation model is Prithvi EO 2.0, and this is something we open sourced. You can find it on Hugging Face, and it's trained on 4.2 million global samples from NASA's HLS. So HLS stands for Harmonized Landsat Sentinel. So Landsat is a satellite constellation by NASA, and Sentinel is a satellite constellation by the European Union, by ESA. And since I told you, the satellites, they are not always at every place at every time. It's better to have more satellites. So they harmonized those in resolution and some other things and created a huge data set of all the images of both satellite constellations. So that's something we are using, and we are also partnering with NASA. So NASA is one of our primary partners here. And we have two models in the EO 2.0 space, which are open source, the 300 and the 600 million parameter versions. And they perform differently. We will see that in a second. And also we added temporal and location information to the models. So we not only show the model the image without giving the model a clue where and when this image has been taken. So we just add this information in addition. So auxiliary information which the model can digest. And then another thing, we do extensive benchmarking now with GeoBench. GeoBench is also an effort which is part of the AI Alliance. It's IBM and ServiceNow at the moment, and they have defined a set of data sets and a protocol how to benchmark different foundation models. So the foundation models are fine-tuned, and different foundation models are fine-tuned, and for different tasks and data sets, you get a certain accuracy score, and then you have basically a list of the best models. So you see here, we evaluate our models using GeoBench, and that means we are having a certain confidence of how good the model actually performs. So you see here the overall performance of our model of Prithvi 2.0, 600 million in the GeoBench. So we are here #1 on overall performance. And you see here in the middle, for the classification, there's another model, other foundation model, which is called DOFA, which has only half the number of parameters. And it's just followed by Prithvi again. And then on the segmentation task, the two Prithvi models are also #1 and 2. So this obviously is subject to change, and that's nice because it's research and competition, and people are just getting better everywhere. So now I want to quickly look if there are any questions. Otherwise, I will tell you something about TerraTorch. Doesn't look like. Okay. So let's have a quick look at TerraTorch. Okay. So this is, as I said, a toolkit, and the question is, before you create any toolkit, is why are we creating a toolkit? There are so many toolkits out there, and obviously we think we need to create one toolkit which unifies all the other toolkits and standards, and then actually there's just one more toolkit on the planet. So that we had in mind, but there is a clear reason why we have created TerraTorch. But before I go into that, let's have a look at the abstraction levels. Okay, At the end, the only thing what you want to do is that PTX and SAS instructions are streamed to the GPUs, no? And that is done via CUDA kernels. They are expressed in a C++-like language and can also be compiled using the C++ compiler and some other compilers running behind it or after it. And that is obviously something you don't want to do if you are not a hardcore hardware researcher. The next level of abstraction in our case is PyTorch. So PyTorch basically gives you tensors and matrices and operations and automatic differentiation and a lot of other things, also some layers. And still everybody implements PyTorch programs a little differently because you have that much of flexibility. So that's why a lot of people like PyTorch Lightning. So PyTorch Lightning just tells you where to put what, you know. So your model goes into Lightning module and your data is served through a data module. And the trainer basically uses those two types and the trainer can be configured. And that's basically how it works. No, there's no need to implement a training loop and so on anymore. Okay, so next thing is for the geospatial world, there is a tool called Torch Geo. And there was a huge discussion whether we want to become part of Torch Geo or if we want to just build on top of Torch Geo. And then we just decided for the moment to build on top of Torch Geo. So Torch Geo is basically also building on top of Torch Lightning, but it makes it an ideal candidate to just add additional classes and types. And that's basically where TerraTorch comes in. And in addition, we do not only support Lightning types, because what we need to do is we need to integrate a lot of third-party foundation models. We don't want to integrate only the IBM ones. We want to have a rich set of all the foundation models. And all those are not always coming as Lightning modules. Therefore, we implemented some wrappers for datasets and for Torch models, and that way we wrap those and can easily integrate it into TerraTorch. So in TerraTorch now you can define your model architectures without code or with minimal code. That's your decision whether you want to go for a config file or you want to go for the Python API. And the other thing is what we have is built-in hyperparameter optimization. This is a plugin called TerraTorch Iterate, which is built on top of Optuna. And the output, what you get is MLflow compatible files. And you can also use RayTune if you want to scale, but there are other ways to scale. And as I said, we have a collection of models. So either source code copied into TerraTorch or wrapped third-party models where you need to pip install the model and the wrapper picks it up, whatever is making more sense. Now, if the model has already a home, then we take that one, and say pip install. If it doesn't have a home because it comes from some research work, we can just give it a home and integrate it as code in TerraTorch. We are Apache 2 licensed, so that's not a problem. And then to build the models, so as I said, we have the backbone, and then you add decoder and different heads for the different tasks, classification, regression, segmentation, object detection, and so on. You need to compose the model, and that is something done by the model factory, and the model factory just takes a bunch of parameters and then gives you this model pre-built, how you define it. And that's pretty neat because you can, since those are only parameters to the factory, you can easily also add those to your HPO search space, and therefore what you're doing is finally a neural architecture search, because you can swap out different building blocks of the model you create and make this part of your HPO search. It's pretty cool. Okay, so here we have our GitHub. It's at the moment hosted at IBM. We wanna eventually go into our own org, but for now it's in IBM, but it's Apache 2 also. And we welcome contributions from third parties and contributions in any sense, no code or issue reports or participation in our weekly. No, we have two community calls per week on Tuesday and Thursday. We have a Slack, so just join the discussion if you are interested. Okay, so it's pip install TerraTorch. We released version 1.0, which we call enterprise ready last Friday. And yeah, let's actually have a look at some demonstrations. Okay, so hopefully this recovers. Give me 1 second, please. Because I changed the network and then VPN. Yeah, was disconnected. Okay, so is this? Oh no, sorry, this is not the correct one. Just a second. Yeah, that's correct one. Okay, so this is now, you see here from the URL, this is running on one of our HPC clusters. And we have here Jupyter Lab, which we can access remotely. And at the moment, this kernel, Jupyter Lab kernel is bound to one NVIDIA V100. The reason it's a V100 is because most probably the request for the A100 80 GB is still pending. Let's double check. Fix the size a bit. Yeah, see, waiting for dispatch. So I was actually requesting what you can see here is a A100 80 GB, but I wasn't fast enough. But that's okay. We are running on a V100, and most of the stuff runs actually on the V100. So what we do is let's actually clear everything and restart the kernel. It's always a good idea. And then let's make sure that the GPU is free. Okay, let's start a new terminal. So CPU usage 0%. Okay, so it's ours. And let's have a look at this notebook. So this notebook here explains you how you fine-tune a model. So you have here, we install a couple of packages and import those. And this is a self-contained notebook. Now, if you have the notebook and the empty virtual environment, you can just execute one cell after the other. It will install all the required dependencies. You at least need a GPU with 16 GB of memory. So if you are on Google Colab, it will work. The T4 GPU has 16 GB of memory. Also, that the V100 has, I think, 32. In this case, so we are on the safe side. And you see here we are downloading data, but this is already done. So this basically will skip. So we can skip over that. It will anyway not download and not extract the data. But what we should do is we should have a look how the data set looks like. As I said, the fine-tuning task requires labeled data. So labeled data. So what we see here is, so by the way, Burn-Scar is a data set which has raw images. And on the mask, you see the burn scars. Now, when there was a fire, we can detect the burn scars. I show you later a couple of applications for those fine-tuned models that it makes more sense. But this is basically the arms and leg work to actually come to the point where you can really make create value out of that insights. No, okay. So you have. So let's consider you have a couple of labeled data points where the burn scars are labeled. So that's the mask. And you see here the mask.tif that's black and white, and you see basically know where the burn scars are. So what you see here now, the cool key feature of TerraTorch. So we have here data modules, and what you see is a generic non-geosegmentation data module. So we deviate from the idea that there is a one-to-one mapping between the data module and the data set. So we have categories of data sets, and in this case, it's a segmentation data set. And what you see is a lot of parameters you pass to the constructor of the data module. So the batch size, number of workers, classes, it's two classes. No, it's either burn-scar, not burn-scar. The train, validation, and test folders and labels. So it's all the same folder here. But since everything is the same folder, we have here the split files. So there are different ways of doing it. You can have split files, or you have file name patterns. So you see here, we also support file name patterns. For the images and the labels, there's a grep or filter string. And then there are transforms. We do augmentations, default, that's random clips and rotations. That's just data augmentation. And then there's a type conversion. We need to transform to a torch tensor, because I guess initially it's a NumPy array or something. Then, since we do not run any validation and tests, so there are no transforms. And then the other thing is we do normalization. So we have computed the means and standard deviations of the whole data set, and we pass those, and we subtract the mean and divide by the standard deviation. So that's a way to normalize the data. Okay, then we can set up this data module to fit, which actually allows us to run training. Don't know whether I executed it cell. No, I didn't. So let's execute that cell. Okay, that's fast because it's lazy. No, it's not doing anything. Let's have a look. Those are the number of images we have in there. And what you notice is it's a fairly small number. No? So we have trained on millions of images, but this fine-tuning task needs only 524 examples. And that's one key feature of foundation models, because the backbone is already pre-trained. It has a good grasp of the underlying nature of the data. So if you are using the same or similar type of data, the backbone actually does the job for you. That's why it's called fine-tuning. So validation we have. Let's have a look at how these images actually look like. Okay, so on the left-hand side, it's the input the model sees. And the middle is the label. No, it's not black and white, it's red and blue, but it doesn't matter. It's basically 0 and 1. No? To be precise, and then it's just a merge. It's not any model doing anything, but you just see here, and it's actually hard to tell, from the image that there in the middle is a burn scar region, but that's ground truth. So now we switch to test here, and now we are doing the fine tuning. Okay, so what you see here is the trainer. Okay, so this is a PyTorch Lightning trainer, stock trainer. We didn't change the trainer, and what we give the trainer is basically two things. Sorry, it's a trainer, and then one thing more. We need to pass a task to the trainer. So that's an implementation interface also coming from Lightning, a task. And this is now also a generic task. So you remember we had a generic data set for a specific task, in this case segmentation. So no need for writing up a data module every time you have a new data set. And the same is here for the task. There's no need of writing up a new task for each, let's say, task, because you're running a semantic segmentation task. So you can use the template implementation of TerraTorch. And no code needed. You see here, the only thing what we're doing, we are passing information to the constructor. And now it's getting interesting, because the first parameter is the model factory. So that's some sort of decoupling, because for different models, we have different model factories. So you pass the name of the model factory, and then the model args are basically the parameters to the constructor of the model factory. And you see here the first parameter to the model factory is the backbone. And the backbone you see here is a PretVEO version 2300 million parameter. Okay. Then what else is interesting? Yeah, by the way, in geospatial satellite data, there are more than just 3 bands, red, green, blue, Depending on the sensor and satellite, there are up to 250. For Sentinel-2, I think there are around 15, 16, and we're using just a subset of those bands. So therefore, we need to tell which bands we are using. And another thing which I didn't mention, TerraTorch introduced another cool thing. So there are different neural network module types. You can compose your model of, obviously, the backbone. Then you have the decoder, which is also, there are different decoders like a unit, a UConnet, and so on and so on. And then the heads, no classification, regression, object detection, and segmentation hits, for example. But sometimes for example, the decoder and the backbone are incompatible in the sense of the data layout. And therefore, we introduced necks, the backbone, and then you have the necks, and then you have the head, kind of, And in the necks, you can reshape. You can reshape and do a lot of interesting things. And we have a set of useful necks you can use. And you see here, there's a unit decoder, and then here's a classification head, and some other hyperparameters. Let's actually run this. Okay. So my TensorBoard is making trouble here in this environment, so we don't see TensorBoard, unfortunately. But now actually the stuff starts. No, so this is the trainer we initialized, and we call fit. And here the model is basically the model wrapped in a segmentation task. So it's 2 parameters. It's the model wrapped in the task, and then also the data module. And then the training will start in a second or 2. I should have run this while talking. I just realized. Anyway, are there any questions while we are waiting? Let me see. No, this chance.
Well, questions. Nathan Einstein, and I was wondering if he's in a position to speak. I'd like to invite him on stage, but not sure.
Okay, so you are breaking up, Tim. I just understand someone is going to stage, or what?
Can you hear me now?
Yeah, now we can hear you.
Okay.
We have a couple of questions from Nathan Einstein, and Nathan, if you're in a position to speak, yeah, I'm gonna unmute you. Give me just a second.
Okay, good.
I think. Oh, I can't. Huh. Hey, Dave, I'm unable to unmute Nathan. Do you know how that works? Maybe you have to raise your hand, Nathan.
No, I don't know if that's it.
Oh, I think I'm the presenter. Let me try if I can do it. So Nathan, let's see. If I can... No, I can't unmute Nathan.
That's weird. Yeah. Questions then. Sorry about that.
All right, actually try it now, Nathan. If you want to unmute yourself, go ahead.
Oh, there we go. Can you hear me?
Yeah.
Perfect. Had 2 sort of quick questions. One of them is, it sounds like the set, really curious about the training data set, since clearly that'll really influence the kind of results that you're getting on other data sets. So in particular, it sounded like there's a pretty limited set of satellites that you're using, and they were all sort of harmonized in some consistent way. Something that I've definitely found in my own work is that as soon as you transfer it to a completely different setting, so say different source of satellite data, it behaves completely differently, and you get pretty awful results. So just curious, have you tested those kinds of metrics on other sources of data? And can follow up with a second question after that.
Yeah, okay. So I have a problem here. I have 2 problems. I'm hearing myself. That's okay, cool. That is solved. Thank you. And the second is, yes, we have done it, but I'm not allowed to talk about it because this is something we're going to announce very soon. So just stay tuned. Yeah, I can't spoil it. Sorry. Okay, but yeah, we have.
Perfect. Okay, for me to ask the second one, is that?
Yeah.
Okay. Was also curious, since it seems like in the NLP world in particular, but also vision language models, training on multiple different training objectives has been a huge breakthrough. And as I understood it, you were just focusing on reconstruction loss alone. So I was just curious whether there were reasons for doing just that rather than other self and semi-supervised learning approaches or objectives to try to get more robust embeddings there.
Yeah, we have tried others. So for example, diffusion, but I'm not a hardcore modeler. So this question I would have to ask one of the modelers. But there was a reason, a performance reason, probably, but I can't tell you exactly why they have chosen that. I'm sorry.
No problem. Thanks.
Okay. And then we have DP in the queue. Let me try to unmute DP. Can I do it? I can't.
No,
Can
that's
someone?
me. That's me, actually. I was thrown out of the conversation and then back in. So I have the same question, like, how big of a data set do you need for like a larger backbone like Prithvi?
Yeah, so I need to double check on the matrix, but I stated this at the beginning. It's 4.2. Let me see. It's 4.2 million samples.
For fine-tuning.
Oh, no, that was for pre-training.
And for fine-tuning, like for like a normal binary segmentation, how many images? Because I mean, everything with satellite data, good annotated satellite data is sparse. Most questions. So how small can you get? Is it compatible with the ARCIS implementation of LoRa for SAM2?
That I don't know. We haven't done that measure. So what we usually have is around the lower triple digit numbers of samples. So in hundreds.
Thank you.
Good. Let's see what the training does. It's finished. Good. Okay, so we stopped already after 5 epochs. No, so don't expect crazy results. So we apply now the model and have a visual inspection of what happened. Okay. Yeah, okay. See, I should have trained it for a little longer because the mass is pretty big, but it's a sake of time thing, no? So this notebook is online. You just need to increase the number of epochs. Let me just show you where you do that. I see here. It's 5. You should go to something like 50 to 100 at least. Okay. Good. Then another thing is this is like the code way of doing stuff. But I said you also have the possibility of using config files. So let's have a look at the config file. This looks a bit like this. Now you have here the configuration of the trainer. There are different callbacks. Even you can log stuff to MLflow and so on. Then you have a data section where you have the data modules configured. And you see here the init args are all the constructor parameters. No? So you can have that in the config file. Same for model. You have here the task and the factory and the parameters to the constructor of the factory. It's very similar what we saw in the code. The optimizer. And then you did via CLI. No? So you can just run this. And there's no code needed. It's basically only a config file because the data modules are generic and the tasks are generic. Obviously, the trainer is generic. So it's a zero code way of fine tuning and also for inference. No? You can do fine tuning, which we do now here, but you can also change fit to predict, and then you would do inference. Okay, so I just want to show you two things. One is the HPO and NAS stuff. And then finally, I want to conclude with a little demo on how we use the whole stack in our commercial offering. Just 1 minute that you get the use cases, basically. So let me see where I have this prepared. Oh, I think I lost the connection. Let's do it again. Oh, here it is. It should be here. Okay. Here we are. Okay, so as I said, we have this plug-in to TerraTorch 1.0, which is called TerraTorch Iterate. And this is used for two things. One is, let's say, ordinary hyperparameter tuning, but this expands to neural network architecture search, because you will see in a second you can define the architecture also in the optimization space. And the other thing is for benchmarking. You have this huge config files, but then you can assess multiple backbones or foundation models with a set of predefined standardized tasks and datasets. And after that, you get the benchmark. And that's something you can do with the TerraTorch Iterate. In fact, TerraTorch Iterate is the reference implementation of the GeoBench standard. Okay, let's have a look how this looks like. It was working before, so let's hope for the best. Okay, so what I'm doing here, so this is a job queue. This is LSF, which is IBM workload scheduler for HPC, but most of you might be familiar with Swarm. It's very similar. There's a couple of advantages, but it's basically just giving you the possibility to schedule a script on some HPC node with specified requirements. So let's see if this already ran. But I have prepared it, so it's not a problem. I think it's done. Yeah, you see it here. Oh, no, it's running. Okay. Because this pending job here is still my request for the A180 GB, which doesn't get fulfilled, but this one is running. So we should actually be able to tail the output, and then we should see the output. While we are waiting, let me actually show you the configuration file of such a HPO run. So this is a separate project. We open sourced that 1 or 2 weeks ago. So let's go to config. So, okay, it's relatively straightforward. So it's inspired by the TerraTorch config files, and it's actually some sort of a superset. So you have here the experiment name, that's self-explanatory. And then what you can do is you can run a set of tasks. Those are Lightning tasks. And if you want, you can set default values for all the Lightning tasks you're defining in this configuration file. That's what we're doing here. And that includes here the backbone. In this case here, the backbone or the foundation model is a DOFA model. And then you see here the list of tasks. So there's only one task. And this task now is coming from the specification, or is implemented after the specification of GeoBench. And then let me actually scroll to the bottom. And here it's getting interesting. No, I have here set number of trials to 1, which actually is not doing any HPO, no, because it's just one trial. But you obviously need to increase that number. Okay. But what you can see here is here you define the optimization space. So this is a discrete space with 3 steps, 8, 16, and 32 for batch size, and here it's learning rate range, from e to the power of -5 to 6 e to the power of -5 to 1 e to the power of -3. The type is float, and it will sample. It will sample from that range. Here the same for weight decay. You see here, you can specify here the optimizer, so values you pass to the constructor of the optimizer. For example, weight decay is a parameter of AdamW. Okay, and then also decoder channels, for example, we optimize over decoder channels. And this is now running and should be hopefully, I see here, it's finished. And what it does is it will write everything to a Optuna SQLite database on the file system, and will also create and export the MLflow experiment. So let me just try to load the MLflow UI. If you're lucky, it should open a listener on port 5000. Okay. Okay, I need to create a tunnel. Let's do that quickly. Maybe this tunnel is already up, not sure. Okay, I just reload. Potentially my tunnel is screwed up and we don't see nothing, but that's just for my preparation 1 hour ago. So this is, for example, all the metrics we collect and actually export to file system in MLflow format. So whatever you do in TerraTorch iterate, you can access the Optuna UI, you can access the MLflow UI. Let me just double check if it screws up. Oh no, it's actually working. So the tunnel is still up and running somewhere. Okay, yeah. So that's pretty cool. Now you just have a CLI tool, but afterwards you can browse through the stuff. And you don't need to know anything about Optuna and MLflow. It's the only thing you need to do is pip install TerraTorch iterate, edit a config file, and trigger the job. Okay. And then the last thing I wanted to show is how does this all come together in a useful application. And this is obviously something we deliver to our clients, for different use cases. And one interesting is, for example, a Kenya use case. So you see here an image from a satellite from 2017, HLS. So this is the overlay, that's the base image. That doesn't have any meaning. It's just looking nice, and you know more or less where you are, that there are lakes and forests and mountains and so on. So this is now real data from a real satellite where we know where it comes from and we know the timestamp and everything. And this is the 2017 one, and this is the 2023 one. Okay. And what you now can do is you can run change detection. Let's open the legend. So wherever you have red areas, you see deforestation, and where you have green areas, it's reforestation. So with public available data and public available models and toolkits like TerraTorch and the Preprocessing model and the Sentinel-2 and Landsat data, anybody can basically come up with that. The only advantage here is it's a button click here. You say run inference, and it applies the model to data. Another example is, for example, flood detection. So let's actually have a look. This is the model input, and we can now see the blue regions is the normal water, and the red regions is the flood. And we can also overlay buildings, and that's an interesting use case for the insurance industry, because you can, if there's a claim, you can see if the building actually was affected by the flood very easily, for example. Also, you can run a building damage detection model easily. Excuse me?
This is far from.
To be clear, their legislators look frivolous. The American people, maybe there are.
Oh, I think that's noise. Okay. Yeah. So, and then my last demo was also here. You can make this even more clearer. No, you can say those are assets of interest, for example, hospitals and schools and so on. And then the red ones are the one affected by the flood and the blue ones not. Okay, good. So that's actually what I wanted to tell you. I hope it was somehow useful. And if there are any last minute questions, just let me know.
All right, great. Thank you very much. Let me see. Let me double check the questions here.
There's one raised hand from Mupala.
Okay, give me a second. Give me 1 second here. Okay, Mapala, if you want to unmute yourself, go ahead.
Yeah, good presentation. So you mentioned about like using 4.2 million samples for training. Are these like 4.2 million images that came from NASA, or?
I think those are tiles, not images, because the images is basically they have a specific size and they have tile IDs. So those are quite huge, and then we further tile those down, and then the samples are basically smaller than the actual image we get from HLS.
So what is the total storage capacity that is needed for the 4.2 million samples?
Oh, a very good question. I just can guesstimate. No, I know one image is around 4 GB, and then I would guess we have around. That's a guess. We would have need to add ask the modelers, but I would say we have around 32 patches per image, and then you can divide 4 GB by 32, and then multiply by 4.2 million. But it's just a rough estimate.
Oh, okay. And like within each epoch, how many layers you have?
The model?
Yeah, the model. Yeah, how many layers are within each epoch?
Oh, that's a good question. I don't know. You mean layers, neural network layers, or image layers?
Yeah. I think like when you're training, like the fast forward has multiple layers. So how many layers are there? Like those things can be configured as part of hyperparameters.
So you are talking about the architecture of the foundation model?
Yeah.
Oh, okay. I don't know. There are quite many, but I don't know. We can find out. We should be able to find out easily. Let's say if there are other questions, let's take those first. And if you want to stay for another 5 minutes or so, I can show you. No, you can basically take the model and you can print the model, and then you will see it. I can show you.
That's a good idea. Why don't we wrap up the other questions here, and then if you want to stick around and do that, I think that's an excellent idea.
Yeah. Okay. I'll stay.
Okay, so we do have a couple questions here. Let's see if I can find it again. Let's see. DP asked how, maybe this has already been answered, but how many images do you need for fine-tuning Prithvi? I'm not sure what Prithvi means there.
Yeah.
How many images do you need for fine-tuning Prithvi?
Yeah, it's in the lower triple digit ballpark. So
okay.
100 to 300.
Okay, and let's see. And then I see that, okay. Yeah, looks like we've got somebody who wants a mentor. We've had at least 2 or 3 people who want to join the project, which is great feedback.
Cool.
I think the testament to your presentation. Yep. So I will make sure to connect you to the ones that I've seen here. Folks who are still on the line, yeah, if you're interested in joining the project or getting involved in some way, you can just post your LinkedIn profile, or or link, or you can contact me directly. I think I put my email address up here earlier. I'll post it again. Where did I put it? Oh, I think I had dropped off. Okay, so my email address is dnielsen. Yeah, right there. It looks like, oh yeah, we got multiple people pasting their LinkedIn profile, so that's great. Yeah,
Okay, and just to answer this question, you see here, this is the layout of the model. So let's see. Okay, okay, let's see. Potentially the foundation model is just one line. Let's double check. We are unlucky because that's getting wrapped. So then we have to do some more exercise to find this out. Yeah, that's the head. Okay, yeah, I think that's the problem. I thought it's already done. It will take some more time to get the backbone also printed, because that's the whole thing, and the backbone should be somewhere in here, but just appearing as one or two lines. No, so that doesn't help. Anyway, okay. Any other questions?
Okay, sounds like that's. Oh, go ahead.
Can you have all
Go ahead.
these as examples? Because I let like I'm myself a beginner, and
Yeah.
it would be nice to have more demos of fine tuning and using Prithvi and so on. And especially there were some issues when you want to use unit ++ with it, which were some bugs and it's very trivial things. And it would be nice to have more manuals for it or more demos.
Mm-hmm. Okay, yeah. So we have here the example section in the TerraTorch repository. So we have example configurations you can use, and we have some example notebooks, and also that is the fastest growing one. We want to have more and more of the tutorial notebooks, and those are then used in sessions like this. So actually I also used this first one here. And another thing is, if something doesn't work, is join the community calls, ask there, ask on our Slack channel, and also just create an issue. That's the way we can get help.
Thank you.
Okay, other question?
Okay, I think that's it. Any other questions? All right, I see people posting their LinkedIn profiles in here. Yeah, and again, feel free to reach out to me if you don't hear from us for some reason. But I will share all these LinkedIn profiles with Romeo and take it from there. But yeah, feel free to reach out to me again. I'll put my email address one more time. Okay.
So if you want to contribute, see, if you want to test this stuff, like what kind of, we can just rent a A100 GPU and.
Yeah, I mean, you can, if you have a small data set, then you can run on the GPU, on the CPU, no? And most of our demos, they run on a T4 or on the V100. The T4 you get, well, let me share the screen here. T4 you get on Google Colab, for example, or super cheap everywhere. And let me just show you.
How long it will take to train on T4 versus A100?
So T4 versus A100 is performance-wise roughly double. So it will take double the amount of time. The main problem is memory. You know, if you want to, for example, we have, I didn't even mention that we have a weather foundation model that's 28 GB, and that obviously hardly fits in a 16 GB GPU. No? That's why it's hard. No? But the Prithvi 2 model is definitely fits easily in a 16 GB GPU, and you get that on Colab. So we have all our models on Hugging Face. So if you go to IBM-Granite, and then in the collections to Granite Geospatial, and we go just to, I don't know, for example, this one. This is a good example. For most of the models, we have a direct link. Maybe that will not. Just give me 1 second. Yeah, we have a link here. Try it on Colab, you know? That brings you to Google Colab, and the notebook is preloaded. The only thing you need to do is you need to select the T4 runtime instead of the CPU runtime. And then you run top-down, and it runs through usually. There's no hiccup with Google Colab. And then that's all you need.
So how much time it takes if you use the
You can
T4?
try it. It's on Google Colab, it will take 20 minutes or something.
Okay.
Good. Okay.
And I keep
Okay.
thinking about the physical AI. I think there is some startup like Causal Labs. So do you know what exactly they are doing in this space compared to what you have done?
No, I mean, we also do research in physical inspired AI, especially the idea is in the optimizer. You add constraints. No, you don't explore any optimization space positions which physically don't make sense. So it's just I'm not an expert on that, but from what I have learned, it's tweaking the optimizer to comply to rules and laws of physics to save on exploration of the optimization space, which doesn't make sense and doesn't lead to a good optimization trajectory in the optimization space. That's how it works, as far as I can tell.
Yeah, I think they are doing physics-based models.
Yeah. I mean, that's one thing. No, you add maybe the laws of physics into the model via optimizer constraints, and the other thing is you learn physics. No, you learn physics for our weather foundation model, for example. We learn the climate physics by observing climate data, and our weather foundation model learned that physics without us even knowing. No, it's pretty impressive. Okay, good. So maybe we should call it a day.
Yep. Okay, we're over time here. So thank you very much, Romeo. This was great engagement, folks. Thank you for joining us. You can follow up with us on the emails that were mentioned down below. Or Romeo, is there a way in which you'd like to be contacted if somebody wants to join or get involved in the project?
For the project, just go to the TerraTorch GitHub. There is a link to the community calls and the Slack. That's the best way. And just create issues if you have issues, and create pull requests if you have code you want to contribute. And for contacting me personally, I'm on LinkedIn. Just
Okay, great. All right, folks. Thank you, everyone, for joining. Hope you have a good day or evening. And we hope to see you next week. We'll have another office hours. And I'd love to continue the conversation. Thank you.